Alrighty folks, welcome back to Swift on Sundays. I hope you are all doing great. I'm ready for some more Swift action. We've got stacks and stacks to get through today, so I'll just briefly recap the rules. The main one is, of course, no harassment, so I have this chat window which you'll see shortly on the right of my screen, always visible in there with lots of questions, lots of hellos from folks. Hey Christian, how you doing? So that's great, but please, no harassment, no bothering folks, no abuse in there whatsoever. You will get an instant ban. So I have no patience for that at all, no tolerance. So please be nice to folks in the chat window. That's pretty much it for this time. I've got to get right in. I've got so much to get through. So my hope today is to walk you through an application that I built to generate a word search. And I've done it previously. I think I did one for like the advent of Swiftmas, I think last year, the year before. But I made one for day 15 of the 100 Days of Swift. And it was great. It's a really great experience because it's making a word search is basically writing a really fun algorithm, and it's a brute force algorithm which is remarkably effective. If you've completed day 15's word search, you will know it really hides words in there effectively. It's a great algorithm. So today I want to walk you through the code required to build this. So we're making an app that builds word searches. That's the plan. But that's one part. The second part is, of course, I want to show you how to render stuff to PDFs, because it'll output a finished PDF word search of the thing, so folks can print it out and do it on paper as the old school similar thing. Even better, we're going to make one that's a bit sneaky, because if you think about like a classroom full of kids, and the teacher wants to hand out a word search on, I don't know, Roman history. What they don't want to do is have the kids cheat by looking over and other kids and saying what they've got going on. So we're going to make one that generates 20 or 30 or however many pages of unique word searches with the same sets of words, so every child has slightly different word search to complete, so they can't cheat. It's impossible to cheat because every word search is completely different, basically. That's the goal. So there's stacks to get through. Just for extra bonus lols, I'm going to throw in a few quick tips on functional programming, so you can really see how you can condense larger amounts of code into smaller amounts of code that's smarter and better using functional coding. So that's the plan. It's a really big project. I hope we can get through it all in one sitting. It is 10 past 6 now, more or less. So I'll go as fast as I can, reasonably, and we'll see how we get on. This is a short version. If you have questions, please do ask as we go, if they're on topic. If you want to ask me about my views on Flutter, which people do apparently every week, that's fine. Leave that to the end, and I'll get to it at the end. Otherwise, I promise you, it just creates massive speed bumps for me as I'm trying to explain Flatmap or whatever on the way. Someone goes, "Hey, what's your view about UIKit on the web?" It's a massive speed bump. So hold fire on the off-topic questions and stick on topic if you will be so kind. It'd be really, really helpful to me and hopefully to other attendees as well. If that's all I have to get going, I'm going to go ahead and share my screen and we can kick off. So I'll press full screen. You should see that. Where is the chat window? Over here. I think my resolution's set slightly differently this time, which is unhelpful because it's clipping the right edge of my screen. That's all right. There you go. You can see the most important stuff. That's what matters. So I'm going to go ahead and create a new 100 Days of Swift. Sorry, I see questions already. Questions that are not on topic, leave to the end, please. Thank you very much, Xavi. Thank you. I'll go ahead and create a new AXGo project. And boom, there we go. Slide it into there, make it fit on the screen because the resolution isn't quite right. I'll choose single view app. And in here, I'm going to call this thing, let's call it word search. I'm feeling real creative today. We'll call it word search. And I'll press Swift, unit tests, fine, next, and create, fine. Okay, so we've got ourselves a new single view app. I think you can all see that on the screen, I believe, hopefully. Looks like it, looks good to me. A little bit bigger, there we go. I think that encapsulates the full width of what you can see. Yep, okay, great. So we'll kick off with the real simple stuff. We're going to create a new file. We're going to put all our code. Now, in theory, there should be like 5 different files, but I'm live streaming. We're short on time. I'm going to go as fast as I possibly can. I'll create a new Swift file with Command N and call this thing wordsearch.swift. Not Swift, capital S, I think. I'm not sure. Capital S? Yeah, okay. Capital S. And in here, we're going to create the basic types required to make our word search function. Now, in practice, this means having a number of different enums and structs and similar outside of the main thing that generates word searches. Things that we can reuse again and again and again. So, first things first, we're going to decide how we're going to try and place words. Now, in an easy word search, you might say go left to right or up to down. In a more advanced word search, you might say go diagonally in some directions. We're going to make it optional here and let folks choose, but we'll make a number of options. One is left to right, one is up to down, one is right to left, so backwards, one is down to up. Then we'll do top left to bottom right to bottom left, and then in really hard ones, bottom left up to bottom right up to top left, and then bottom left up to top right. So the really hard ones are like going backwards and upwards at the same time. Anyway, point is, these are different kinds of placements we're going to work with. So I'll say enum placement type, and I'm going to use the Swift 4.2 protocol case iterable, which I absolutely adore. It lets us generate random elements from this thing by pulling one out. Give me a random placement type, for example. Or we can say shuffle the placement types and give me the first 3 or whatever. So it's a really cool thing to have for enum cases like this, because we can get random items very easily. So I'm going to say all our cases are, like I said, left, right, up, down, and so forth. So I'll say case left, right, case right, left, so going backwards, case up, down, and case down, up, again going backwards, up the way. Then the diagonal ones, top left, bottom right, so going sort of diagonally down the way. Then case top right, bottom left, so going diagonally down the left the way. Then case bottom left to top right, and then finally case bottom right to top left. That last one being the hardest one going, because it's sort of up the way and going backwards, so it's awfully hard. So that's our different kinds of placements we want to put our words into the word search grid. Now each of those can be represented as a series of movements. Like we're going left to right. We're going to say our X movement is X1, and our Y movement is 0. It's going to move 1 to the right each time as we're placing left to right. And going right to left, X will be -1 and Y will be 0. We're going to go -1 each time as we're placed. Up to down, X0, Y will be 1, going down each time by 1. Down up, -1 for Y and so forth. But get the idea, you can represent each of these placement types as a series of movements. So I'm going to add a movement property to this thing. And it's going to be a computed property that returns an X int and a Y int. We'll say switch self. If we are case left right, then we're going to return 1 0. So move 1 to the right each time for each letter in the word as we're placing it, but not at all upwards. And then we'll do case dot right left. This is going to be the opposite, so going left 1 each time rather than up and to the right. So we'll do return -1 0. Let's move down to a little bit. There we go. For up down, we're going to say return 0 on the x-axis, stay fixed where you are on the x-axis, but go down each time by 1. So we'll return 0 1. Then for down up, we are going to, oops, I'm missing a colon there. We're going to return again 0x, but -1 for the y. So it goes up 1 each time it places a word in the word, letter in the word, sorry. For top left, dot top left, bottom right, it's going to go right 1 each time and down 1 each time. So we're going to say return 1 1. So move down and to the right every single time it places a letter. Then case top right, bottom left. This is going to start at the top right and move to the left. So it's going down still, but going to the left this time. So it will return -1 1. Then bottom left, top right. This will return 1 -1. Starts on the left, goes to the right each time, but also goes up each time. So -1. And finally, case dot bottom right, top left. This is going left and up each time. We'll do return -1 -1. So that's a series of placements we can have for all our movements we can have one placement. So that is the first enum we're going to have. The second one is going to define how we work with these things. Which ones do we use for any given game difficulty? Because you might say, listen, these kids are only 8 years old. Let's make it just left, right, and up, down. or more advanced kids, 18, whatever, you might say, I want every possible direction. So we'll say enum difficulty, case easy, case medium, or case hard. And it's got to be one of those three, ultimately. Is it an easy word search, a medium word search, or a hard word search? Question from Suhaib. I'm building the whole functioning app here, or as part of a series. My goal is to get through a whole app, which is why I'm going at 11, gear 6 right now. I can get maximum speed right now and hope I can get through it in one session. If I can't, it'll be 2. My goal really is 1. Otherwise, it's very annoying, Wait a whole week for part 2. No one wants that. Anyway, so we now have easy, medium, hard difficulties. We're going to make this thing say, for a given difficulty, which of those placement types do we want to use? So I'll say var placement types is an array of placement type. Switch on self again. And we'll say if we are in easy mode, we will return just .left, right and .up, down. But we're going to shuffle these things. So each time we get a different array of things. It could be up, down, left, right, or left, right, up, down each time. Different every time. Then we'll say case, lowercase c, case.medium. In medium mode, we'll use left, right again, and up, down again. But we're also going to add in .right, left, and .down, up. So it can go backwards in either direction now, but not diagonally still. Again, we'll shuffle them up. So every time we ask for this thing, it'll be different. Let's make a bit more space. There we go. Then finally, for default case, i.e. hard, we will return all cases. So we're going to say return .left, right, .right, left, .up, down, .down, up, .top left, bottom right, then top right, bottom left, then bottom left, top right, and finally bottom right, top left. Again, shuffling that. Now, I believe I made this thing case iterable, I think, which should mean I can actually just do return placement types dot all cases dot shuffled. Did I make it case iterable? Let's find out. Oops, return just that last bit. There we go. Let's try that. What does it make of that? Has no thing called all cases. No, I did make it case iterable. No, anyway. Sorry, capital P. Sorry. There we go, that's why. Even better, hopefully. Nope, still not sure about it. Placement type, there we go. There we go. Thinking very carefully, Xcode. Thinking very carefully. Yeah, that's worked great. So you could have, of course, type them all like I did there, or just use all cases. I prefer all cases, but you might want to change your mind and say, okay, maybe bottom right, top left, too hard, whatever, and take that one out. Whatever one works for you. I prefer to use all cases. Whew! Okay, so now we've decided all the possible ways we can place words in our word search. That's the placement type enum. And we've got an array of an enum of difficulties saying if you're in easy mode, use left, right, up, down. If you're medium mode, left, right, up, down, whatever, down, up. If you're in hard mode, return all possible placements and shuffle them out. Yes, Robert, question, Robert, can I use .hard? I absolutely could use .hard. Absolutely could. Like that's fine. That works well too. So we've got this, both our enums now, determining how we place words in a grid. What we haven't yet got is a concept of what a word actually is. Question from Javon, it does not have to have a default case. It just has to be exhaustive. It has to cover all possible switches. And easy and medium hard does cover all possible cases, so we are quite fine having that. Anyway, we now have to define a word struct that defines what a word means. Because ideally in a word search, not in this case, but in the future, you might want to say, here's my word to place, and here is my definition to look for. Now the definition could be the word itself. That's what kids' word search normally have. They have things like, find cat, find dog, find hamster in the word search. In the Swift 100 Days one, I actually gave a clue string they had to try and guess. So they'd see something like, a set of rules that constrain how a type must be implemented. And they've got to look for the word protocol in the word search somewhere. So you can do both, whatever works for you. I'm going to say we've got a new struct, word, and this thing has the text we want to place as a string, but separately a clue, what to look for in the bit at the bottom. Now that clue, like I said, might be, var. That clue might be the same word if you're doing it for kids, but if for adults and you want more advanced stuff, fine, you would use a clue string like we did in the 100 Days of Swift. So that is our word struct. I'm going to make one small change to it though, because we want to load this thing from some JSON. Rather than typing it all into code, we're going to put it into a JSON file and load that into our project. So we'll say struct word is decodable. Decodable. So we can decode this thing from JSON. Whew. Okay. Those are the main types we need to use in our word search. I'm going to stop and take a drink. That's a lot of work already. Phew. That's like 60 odd lines of code already. Don't say you don't get maximum value for money out of these things. There's only 10 minutes gone by. Anyway, now it's time to define the main element of this game, which is the word search we'll be working with. So I'm going to say class word search. Now I'm making this thing a class because I want this thing to have lots and lots of mutating functions, and having struct with mutating func all the time is very annoying. So I'm being lazy and making this thing a class. It could be a struct if you want it to be. Doesn't really matter. I'm going to say var words equals an array of word. These are the words we expect this thing to be created with. So, you know, look for cat, dog, hamster, whatever. That's the words array. We'll also give it another variable, property, sorry, called grid size. How big the grid should be. I'll give it a default value of 10, which is fine in a testing mode here. I don't want to be sort of staring blankly at word searches while you're watching me try and solve it. That'd be embarrassing. So making a 10 by 10 grid actually works quite nicely for a live stream because it's small enough even I can find words very easily. Now when it comes to the labels in our word search, actual letters in the squares themselves, we can't just use strings here because we want to modify these things from a number of places and read them from various places. We actually have to make these things a reference type. Now, if you aren't aware, value types always have exactly one owner. If I have a string and I say, you know, var a equals Paul, and take a copy of that string by doing var b equals a, b will get a copy of a. So if I change a, b won't change. They have their own unique copies. Reference types all reference the same bit of RAM. That's what they're called, reference types. And class the reference types, and for bonus points in the chat window, you can tell me the other reference type in about 15 seconds when this thing finally catches up. You can go ahead and tell me the other reference type in the chat window. Oh, it's Sean. Hey, Sean. I'm looking forward to your talk so much at iOSCon. Anyway, the other one is reference type. Now, in this case, we want to be able to modify our word search labels in various places, and you'll see why later on. And to do that effectively means having a reference type. So it's going to be a character on the string. We can have a letter on the thing, but we want to wrap that inside a class so it's a reference type. So I'm going to actually say up here, class label contains a letter character, which is by default an empty space. Now, it's a reference type again, so we haven't got to worry about it being mutated freely. It'll be fine across the board, which is great. So, down in our word search thing, we can now define our grid. Now, a grid, of course, is a two-dimensional array, an array of arrays. I'm going to say var labels equals an array of label. So a two-dimensional array, like that. Then we'll say our difficulty is going to be difficulty.easy. Varanch, that's a good question for later on. Amit, right answer. Closures are the other reference type. Well done. Difficulty is easy mode, because otherwise I'll be staring blankly at the screen trying to find words, which is a bad thing. We'll do var number of pages to render will be 10 by default, but we can modify that later on, of course, to be 20, 30, however many in the class. And finally, we want a way later on to fill out a grid of random letters. Now, I looked for a good old while and just tried to figure out a nice way of making random letters in Swift. And I couldn't find a nice way. I genuinely couldn't find a nice way of making random letters. The best way I've found is this. Let all letters equals 65 through 90.map character unicode.scalar $0. So 65 through 90, if you weren't aware, is the ASCII symbols, ASCII numbers for capital A through to capital Z, as 65 through 90. And we can create a scalar from that with Unicode scalar as $0, so 65, 66, 70, up to 90, then wrap that in a character. So this will end up being an array of A to Z as characters. That's my best attempt at making a nice array of letters in Swift. If you've got a better approach, I'd love to hear it. Not one that makes you type A, B, C, D, E, F, G by hand. I don't want to do that. Thank you very much. Whew! Okay. At this point, we have all the properties required to make our word search. So we want to go ahead and make a method that actually generates the grid. Now this is going to do a number of things over time, but for now we're going to make it really, really simple. First, we'll initialize our two-dimensional array with a load of labels. Then it will fill all the gaps, give every letter a random letter, A, B, Q, whatever, and then print out the grid. So we're going to say func make grid. Then we're going to start off by initializing labels to be an array of arrays of labels. So we're going to say 0 up to excluding grid size dot map underscore in. We don't care what the actual number is, underscore in. In there, we'll do again 0 through grid size dot map. Oops, dot map. Again, don't care the value, return a label, like that. And that all being well, we'll think about it. So label in label. There we go. That will create our two-dimensional array of labels. This thing will count from 0 through grid size, so 0 to 10, excluding 10, so 0 through 9, and make a label each time, put that into an array of labels. And that itself will go round as many times as we have grid size. So it will make an array of arrays, like that. Nice and easy. I can't think of a nicer way of doing that in Swift. So it has this thing which is you can do string repeating something like 5, count 5 times, and that kind of works. But the problem is it repeats literally 5. It doesn't copy each time. It uses the same instance each time, and we want a new instance each time. We want a label each time as opposed to the same value each time. So we can't do that, I'm afraid. Anyway, that will make our two-dimensional array of stuff. The next thing we're going to do is call a method we haven't written yet called fill gaps. Fill gaps. So that will go through, find all letters that have no value right now, and give them a random letter from our all letters array. And finally, print grid. This is just a debug function that will print the values in the grid so we can see visually ahead of us what's actually in the grid. Great for debugging purposes, trust me on this one. Whew! So, the fill gaps thing is trivial, right? We're going to go through all the rows, go for all the columns, find if there's a empty string in there. If there is, give it a random letter. So I'll say private func fill gaps for column in labels, for label in columns, because remember it's a two-dimensional array. I'll go over both the arrays. Oops, in column. Go over both the arrays inside there, so it's a loop inside a loop. If label dot letter is equal to an empty string, then label dot letter equals all letters dot random element. Okay, ROL does not have done anything at all. I will briefly recap. I am going very quickly. There's so much code to get through, about 300 lines potentially, so I will briefly recap. So far, what we have is we have said here are the different ways we can place words. For a given word, it could go left, right, or right, left, or up, down, or down, up, whatever. These are the various directions a single word can go. Once we know that, you know, it's going up, down, or down, up, whatever you want to, we can then decide how to place that word. That's the movement. We can say, if we're going left, right, every letter we place, go right one place, go right one place, go right one place, go right one place. So to place the letter cat, place, go right one, place, go right one, place one. That's all 3 letters placed. That's left to right. Going right to left, we have -1 for the X. So we go backwards. We go place a C, go left 1, place the A, go left 1, place the T. That's right to left. So it's going -1 each time in the X. But always 0 in the Y. Don't move up and down. For up down though, we have 0 in the X. Don't go left and right, but go +1 each time. Down 1, down 1, down 1, down 1. And for down up, it's the opposite. Up 1, up 1, up 1, up 1 as we place in letters. So that basically each of these things represent the various movements required to place in those directions. That is our placement type enum at the top here. The second one is the enum difficulty. We have 3 of these things, easy, medium, hard. And it will say, for a given difficulty like easy, you have left or right, or up and down. Or for medium, you have left, right, right, left, up, down, down, up. Or for hard, all possible cases, so use all directions. All 3 of them, though, shuffle their values. So they'll go in a random order every time to make sure the thing is completely random. Otherwise, the word search is predictable. No one wants that, right? So that's our 2 enums. Next up, we've got our word struct. This holds an actual word to place on the screen. So it'll say, the text is fine hamster. The clue is small furry creature that likes eating vegetables. Whatever. Or could be the word hamster for kids, whatever works. For the class label, what's happening here is, as you'll see later on, when we try and modify our letters, we want to be able to modify them in place and say, this exact letter in the array, modify that to be Q, whatever. And if it's a value type, we couldn't do that because it'd be a copy of something else. We'd have two different letters existing in the array, which is what you don't want. As a reference type, sorry, the class, if we modify one instance of label, any others that point to the same label will modify it automatically. So they all point to the same thing. Anyway, and finally we have our main word search class here. Has an array of words to render. So hamster, dog, cat, whatever. The size of the grid, so 10 by 10, 12 by 12, whatever. Has a two-dimensional array of labels. That's two-dimensional because it goes across the way to the top row, then a second row, third row, fourth row, fifth row. It goes in two dimensions like this. I'm using easy by default because I'm lazy, and it'll do 10 pages by default because, again, it's easy enough. This thing is a bit of a hack. It's my attempt to get a random array, of all letters that you can use in the alphabet. So it'll contain A, B, C, D, E, F, G, up to Z as an array of characters. There's no better way of doing that, I think, but that's my best solution so far. Make grid makes our two-dimensional array of labels, so it'll create a label, 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 label. Next row, label, 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 label. Next row, label, 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 da, 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 until it's full of labels. Then it will fill all the gaps. It'll go through every letter in the label, sorry, every column in the label thing. So it'll go through the first column, second column, third column, fourth column. And then for every label inside the column, so it'll go down the rows, it'll say, are you empty? If so, have a random letter. Whew. That's my speedy re-explanation of what we have so far. Christian diacritics, sorry. You can modify this in your own time to have all the Polish you wish to have. Anyway, that's our fill gaps method. It'll create a random grid. That's what it's doing. Finally, we have to implement private func print grid. And it's going to say for column in labels, then for row in column. So again, we're going to navigate through the entire two-dimensional array. We're going to say then print row.letter with the terminator being an empty string. Don't make a new line after every column. But after every row, do make a new line. So that should, in theory, print out each row in a one big line of text. Like that, and then do each column at a time. Hopefully. We'll see. Whew. Okay. To try it out, of course, we have to actually make one of these things and use one of these things. I'm going to go over to viewcontrol.swift. And in here, I have to actually make an instance of our word search class we've just defined and give it some stuff to load. Now, I have pre-made some JSON. It is over here off screen slightly thanks to my resolution being wrong. If I drag in capitals.json into my Xcode project, I'll show it to you. But boom, it looks like this. Called capitals.json. It'll be on GitHub when this project is uploaded. And you'll see, oops, I've written card for the case. You'll see it is a list of text and clue elements, just matching our word struct. So we have London is the capital of England, Edinburgh is the capital of Scotland, Belfast, Northern Ireland, Cardiff, Wales, Paris, France, Rome, Italy, all the way down. Lots of example capital cities in here, including Christian Poland. Haha, I totally didn't miss you off. Anyway, lots of capital cities in here from places around the world. We want to use that for our word list, for our word search. So, over in viewcontrol.swift, the first thing we're going to do is grab that JSON file out, get it into a data instance, and convert it into our word array. Now, in previous Swift on Sundays, I have shown you how to do this nicely, using, a nice extension on, bundle I think we used to load it, decode it all very carefully and so forth. Here, I'm totally going to be lazy, and I'm going to just force it all through. I'm Bishan, Belgrade's wrong, it's not Portugal. What did I type? Belgrade. Oh, yeah. Sorry, I put in Belgrade, Portugal, Belgrade, Serbia. You're absolutely right. Sorry. There's my geography failure for you right there. Yes, thank you. Sorry, I fixed it. Yes, no, sorry. My mistake. Anyway. I've shown you previously how to load this JSON and decode it beautifully, okay? This time, we're not going to do it again. So I'm sick of repeating myself, quite frankly. So I'll do it the easy way, sorry. We'll do let path equals bundle.main.url for resource. Here, we'll say capitals with extension JSON, like that. I will happily force unwrap that because I'm being lazy. Let contents equals try. Again, force that one through. Contents of, lowercase please, contents of is going to be, oops, equal sign there. Contents of path. Again, I will go to there and then say let words equals force try. JSON decoder dot decode array of word dot self from the contents. Boom. Again, please go back and see earlier Swift on Sundays for a much nicer way of doing that without all the exclamation marks. Do that in your own code. We can now make a new instance of our word search struct. So I'll do let word search equals a word search. Word search.words, I've got an error somewhere, equals words. And finally, word search, say word search.words. And finally, word search.make grid. Now, what error did I make? Let's find out. Oops, yep, capital W. Is that it? Is that it? That's pretty small. That's pretty small. Hey, well, that's like, whoa, 25 minutes of coding and only one small error, apart from the whole Belgrade fiasco. Rats. Anyway, I'll run the code. It's going to sit and launch the simulator. I look younger every Sunday. Yes, it might be the wine. It might be the wine. It's certainly not my kids who are, of course, doing lots of interesting things with me in my life. Class name capital. Yes, thank you, G Palooka. I fixed that one already. Anyway, it's going to try and build and run our thing. And hopefully, we're going to see a printout of our thing. Now, it's currently not doing anything. Cool. Come on, iOS simulator. There we go. Phew, just took a little while to get going. Come on, you can do it. I can't move the screen, mind you. It's slightly annoying. Bye, Sean. Ah, Sean has given me my money back with $1.50 missing. I gave him a super chat last time. Damn it. Inflation, Brexit, one of the two. Anyway, it is now run. And what you'll see, all being well, in Xcode down here, bada boom, is our random grid. Our random grid. So it's showing lots of letters in here. I should say this thing is not ordered by letter frequency. So A and X and E and so forth are equally likely to happen, which isn't ideal. You want them to be, vaguely realistic. So, more E's and more I's and S's and similar than you would get with X's. But it's a start. It works. Point is, we've got a grid. That's the main thing, right? That was the easy part. That frantic typing was the easy part. The actual hard part, the next part, is placing words in an intelligent, useful way that actually makes for challenging grids. And that means going through all the words we just loaded from our JSON and placing them on the grid in a random variety of directions. So we're going to go through and say, for each word, try all directions randomly. So it could be left to right first or up down first, whatever. It's random every time. So the grid's really quite challenging. But then for each direction, we've got to try and place it in random places on the grid. We don't always start in the top left and then work out the way, otherwise our grid will be very heavy on words in the top left corner and really vague on words in the bottom right corner. So we want to try and place it in random places using random positions and similar. And we can know it's possible to do that by going to a location and then reading all the labels it will touch and say, okay, if we're going to start here with movement type up, down, read that label, read one up, read one up, read one up, and so forth, for the whole word, and if they are all valid, then we're good to go. We can return that array of labels and say, modify those, please. And because we're returning an array of labels, that's where our reference type comes in handy. So we have an array of arrays over here with all the labels, and a function over here that will return a new array of labels based on the ones from this array. It'll say, okay, these 5, modify these. And if our label type was a struct, the labels here, here, and here would be different instances of objects. It wouldn't be the same thing. If we had classes, we do have classes, they point to the same labels. So modifying them in this array modifies them in this array as well. That's a really, really helpful thing to do in this instance. So the smart way to do this, the easy way to do it, is to write it backwards. So work through backwards up to a big sort of finishing, hopefully, conclusion where it all magically comes together and totally doesn't fail at all. We'll find out shortly. So the first thing I'm going to do is say, okay, at this position, like, x6, y5, with this movement, moving left one each time, can we fit this word in? Can we fit this word into that space? So from here, going left, can we fit the word? No. Can we go up the way? No, whatever. It'll be called with a position in the grid, plus a movement and a word to fit, and it will return, did this thing fit in that space or not? So I'm going to go to our word search class, which is currently outside our little group. I'll move that into here just for my organizing tendencies. I'll make a new method in here called private func labels from x int. So this is going to be from x. This is going to return the labels at a given position from an x position and a y position. So at like column 6, row 3, find me the labels, please. For a given word string, let's hide this thing on the left. For a given word string and some movement, going left, going down, going right, going diagonally, whatever. There's going to be an x int and a y int. That's what it'll take. Look at this position on the grid, x whatever, y whatever, move in this direction for this word. And it's going to return, if it succeeds, an array of labels. These are labels you can modify to make that word fit. That's what it'll do. If it fails, if we cannot fit the word in that spot, it will return nil. This will be an optional array of labels. Here we go. First thing I'm going to do is make a new empty array of labels. Our return value equals an array of label. And we'll take copies of our x and y coordinates. We'll say var x position equals x, var y position equals y. So we start off where we were told to start off. And now we're going to go and loop over every letter in the word. So if it's hamster, it'll go H-A-M-S-T-E-R and loop through each letter as we go. So we'll say for letter in word. Now we can read out the label from our grid and say, okay, at this XY position, what is the current label? So we'll say let label equals labels X position, Y position. So Plan Andrew's asking why use X int Y instead of placement type. Because placement type will tell us it once. We don't have to go through again and again and call that property every single time. It's not a lazy property, it's a computer property. So it's called every time we read that movement thing, it'll call it. So we want to just get that thing out once and use it again and again for our movements. Anyway, grab the position of grab the label at a particular position on the grid like that. We can now say if label.letter is equal to an empty string, then it means it has no letter in there yet. We can go ahead and fill that with a letter. But also, importantly, if the label.letter is equal to the current letter in our current word, because we can reuse letters. Ideally, we want our word search to aggressively reuse letters. So this way it'll say, if there's nothing there, use it. But if it's there and actually the same letter we already want, it's still good, also use it. If that's the case, we're going to go ahead and return value dot append that label. So we'll say, yes, this grid square, that can be used as part of our word. That's what we're doing there. We can then modify our x position variable by movement.x. So move one place to the left or move one place to the right or stay still depending on the placement type that was selected. And also y position plus equals movement.y. So move by whatever amount we've been told to move after each letter has been placed. But if this letter cannot fit, if it either if it has a letter already taken, like Q, and we're trying to place a T, it can't fit in there, bail out. This direction has failed. We may have got a few letters in already. Doesn't matter, it's failed. Get out of there straight away. We'll do return nil. This did not work. After the loop, if we've made it through all letters in the word, successfully adding them all to our labels array, then we'll return that. Send back, yes, we place CAT here, here, and here in our grid. That's what gets sent back. An array of labels at particular positions saying, yes, here, here, and here, that spells cat or hamster or whatever. That's what we'll send back. So that will place, to be quite clear, that will place one word at a particular XY coordinate with a particular movement. Or it'll try to. It might fail, obviously. It'll try to. Next, we're going to try and write a function that will place one word with a specific direction. We don't care where. We'll try all possible locations, but for one particular direction. So we'll say private func try placing some word string with our movement again, x int, y int, and this will return bool. Did this successfully place the word or not? So this is going to try all possible squares. Try placing it here, 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 all the way down, all places in the array with the same movement. So it'll say, okay, the movement is up to down. Try placing it here, nope, here, nope, here, 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 and eventually, hopefully, it works. But it'll try them all to make sure at least one of them hopefully works. Of course, though, we don't want to start in a top left corner. Otherwise, it will place most of our words in one corner, and it'll be a very, very easy word search. We want to really start in a random position and then figure it out from there. So what we're going to do is we'll say, firstly, we're going to figure out the size of our word in the movement we're looking at. So we'll say, let x length equals movement.x times word.count minus 1. And the same thing for y. So y length is movement.y, word count minus 1. So what's happening here is we're saying, if our word's been placed left to right, and our word is cat, then our total horizontal length of our word is 3. And this will allow us to not place the word off the grid. If we start on the very, very right-hand column, and we're moving left to right, it won't fit. It'll run off the column straight away. The reason we have minus 1 for the word count is because we start at the initial square. So we're starting at square 0, then it will start from 0 and count left to right 0, 1, 2. If it had just word.count, like that, for a horizontal movement, it would have said movement x would be 1, word count would be 3. It would position it from 1, 2, and 3, as opposed to 0, 1, and 2. So you want to do minus 1 like that. So that's the length of our word horizontally and vertically. Now we want to figure out all the possible places we can place this word. We're going to get a random array of numbers horizontally and vertically. We're going to say let rows equals 0 equals 0 up to excluding grid size dot shuffled. So give me between 0 and 9 inclusive shuffled. And the same for cols. So we'll get through, 10, 3, 6, 4, 1, never, random positions for rows and columns. And we're going to try them all to make sure one of them succeeds. So we're literally going to try every possible square for a given word in a given direction. Okay. We'll say, for row in rows, for col in cols, go through both those arrays. We can now figure out the final position of the word. So if we're starting at column 0 and our x length is 5, we'll count up 1, 2, 3, 4, 5. It'll count up and say, okay, you can end here for a given length of words. We can say how big the word's going to be. And we're going to use that to make sure we don't try and place words out of bounds. So if we're starting on the very left column and we're placing a word right to left, it'll go 0, minus 1, minus 2, minus 3, minus 4, and be out of the bounds of our array, which you don't want to do. We want to say, make sure this row and this column is inside the bounds of our array for our word. So we're going to get the final x position of our word by doing the starting column plus the x length of our word, and final y as our row plus the y length of our word. So it'll tell us where this word will finish for a given movement type. Potentially off the grid. Probably off the grid most of the time, bluntly, but potentially off the grid. And we can now use that with a quick check. We can say, is this value inside our grid? So if final x is greater than or equal to 0, and final x is less than grid size, and final y is greater than or equal to 0, and final y is less than grid size. So make sure we are in all four corners of our grid. We aren't trying to move beyond minus 0, minus 2, minus 3, whatever, or beyond 10. So, we know, rows 10, 11, 12, 13, 14 are all banned. That will exclude them all. Don't even try and place the words there. Whew. Now, at this point in line 148, we can say for sure this word fits within the space available to it. Can we actually place it there? And that's what we call the method we just wrote, labels from x, y. We can call that and saying, try and read the labels for this thing. And if you remember, that would return an array of labels if it was placed successfully. If it wasn't placed successfully, then it would return nil. So we're going to use an unwrap here. We'll do if let return value equals labels. From x will be our x column. Our row will be our y. Our word will be just word. And movement is our movement. And if that succeeds, if we get back an array of labels successfully, then we know that word can be placed there. It's able to be placed, either because it's reusing letters or that using letters that have no space and no letter at all yet. So at this point, we can now go over all the letters in our word and place them in the labels. So we'll say for index letter in word.enumerated, return value index dot letter equals letter. So for the word cat, it'll pull out 0 and C for index and letter, then 1 and A, then 2 and T for going around the loop. And I can now set the return value, which is an array of labels. Return value 0 letter will be C, return value 1 letter will be A, return value 2 letter will be T. And this is why it matters that these labels are reference types. Because these return values, these label instances, exist in our return value array here, but simultaneously in our array of arrays over here. And if we had them as structures, they'd be individual unique copies. We could change them here in return value and they wouldn't change here. Because the label is a class, changing them here does change them here. So this code modifying our return value array will actually modify our main labels array as well. It will do both at the same time, which is fantastic. And once that's done, we can say return true. This word was placed successfully because we've gone ahead and got this return value back. If that failed, if we got through all the rows and all the columns and we could not place this word at all, we will return false. This word could not be placed in any square for that given movement type. Remember this function here, this method here, only does one movement type, going left to right or down to up or whatever. Only one movement type at a time, but it checks all squares for that movement type. The next level up, and we're going backwards here, the next level up is to write a method that will attempt to place one word in any direction. It doesn't care about squares, it cares about directions. It's going to go over all possible directions saying try and place a word, try and place a word, try and place a word, with each direction as it goes. We're going to say private func, place some word string, returns bool. First things first, we're going to get a formatted word, which is going to be the word text. Word text. But we're going to replace occurrences of spaces with empty string. So if someone tries to use a space with their word, it'll strip them out automatically. But it will also make the whole thing uppercased. So London will be capital L, capital O, capital N, capital D, capital O, capital N, rather than sort of mixed case. Because words that just look weird. It's a bit easy if there's capital L's around. You can sort of find the place names very easily. So making it all uppercase makes it harder, which is great. And now we want to go ahead and place this word in our grid, or try to at least, with every possible placement type. So we're going to say for type in difficulty dot placement types. Now if you remember, this will return left to right or up to down for easy. For medium, left, right, left, up, down, up, and so forth. But it will always provide this thing to us shuffled each time we read that thing, it'll be shuffled. So each time we call this thing, it'll say left, right, left, or right, left, right, whatever. It'll be different every single time. So we're going to loop over all the placement types we have for this difficulty level we're on right now. And then we're going to say if try placing our formatted word with our movement, if that succeeds, we're going to say return true. We successfully placed that word for this movement type. If we've gone through all movement types, return false. So we're working backwards here. Initially we had labels from. It'll go through every possible square saying, does CAT fit there? No, bail out. One up from that, it will say, for this given movement type, going down to up or up to down, whatever, go through all possible squares in the grid and try and place it there. At a high level again, we have no movement type, no position yet, just a word. Go through all placement types and try and place them all. So we're going up and up and up, higher and higher and higher. And this kind of code's fine. I did promise you a few sort of functional tips here. We can collapse this down to use one of my favorite methods in Swift, which is contains where on sequences. If I comment that code, we can instead say return difficulty dot placement types dot contains try placing formatted word with 0 dot movement, like that. And that becomes our entire method. Now what's going to happen here is it's going to go ahead and call try placing with the first item from placement types, and it'll pass in the movement type for that placement type. And if that succeeds, this thing will return true. So contains will return true, and that'll go back to return and leave place. If it returns false, it'll go to the next placement type, and the next one, and the next one, next one, until one of them finally returns true, at which point the whole thing will return true, and it bails. And if they all return false, contains where will return false. So it's a really, really nice way of doing that same code, just in hardly any code at all, which is great. Whew. Okay, so now we have placing one specific word. It'll go through all placement types, which in turn will go through all locations, and then try and place them all, which is great. I'm going to go one higher. The sort of very top level of our little diving board here. We're going to say, try and place all the words. Go through all words we can find and place them all somewhere. So I'll say private func place words returns an array of word. Which words were actually placed in the thing. So we can then say, here are the words you're looking for. Obviously, it'd be a bit mean if you try and place 50 words, only placed 40 words, but then showed clues to 50 words, right? You've got to try and look at a long time trying to find words that don't actually exist in the word search. Maybe you're evil. Maybe an evil word search generator. Yes, that's a brilliant app idea. Evil mode. Easy, medium, hard, evil. Anyway, in here, we're going to go over all the words in our array and call place on them. Attempt to place these words, which will in turn try all directions, which will in turn try all squares. To do this, we're going to say first words.shuffle, give them a random order of the words, so it's different every single time. Then var used words equals an array of word. Let's scroll down slightly. Then for word in our words array, if we can place the word, then use words.append that word. Otherwise do nothing. And finally return used words. Boom. Hope you're doing well. I would think. Great. Works great. So that will go through and try and place every word in our complete word collection. Shuffle link though, so it's different words every single time. That's fine. Again, I did promise you a few sort of functional tips along the way. So let's compact that down to a bit less code. I take all this code here and comment it out. The better way of writing this is to do this. Return words.shuffled.filter place. That's it. Now one line of code does all that. Just more conveniently nicely. So what filter does is it expects to be given a function like place or whatever you want to. And that function must accept one element from the array and return Boolean, should this be in the final array or not. So it'll be called with the first word, return true or false, second word, return true or false, 10th word, true or false, whatever. And our place function, our place method, actually happens to, if you look at it, accept a word and return a bool. So it is a perfect candidate for filtering. We can pass that directly to filter as this, filter place. And what it means is it'll go through, get the words array, shuffle them all, and call filter on every one of them using place. And any that pass place, any that will place successfully, will be in the final value that will get returned back from this whole thing. So whatever this return, place words, will be an array of all the words that were successfully placed, which is fantastic. So I'll go ahead and get rid of this code here. Goodbye, old code, nasty. The new version is much nicer. It's so short, we barely even need this place words method right now. Get rid of the whole thing probably. Anyway, nice to have. So now, the moment of truth. How many mistakes did Paul make while typing this massive wall of code at light speed? Let's find out. Before we call fill gaps up in make grid, we're going to call place words. Try and place the words before we actually fill any gaps. And then I'm going to take a large glass of wine. This might blow up. We're going to find out. Commander, come on. Faith. And we've got a large chunk of stuff. And I can see Belgrade already. There's Belgrade. That's why it's on easy mode, so people like me can see it very quickly. We've got Budapest going vertically down here. We've got Cardiff here. We've got London here. Madrid's down here in the right column. What else we got? There's probably some more I can't even see that you could probably seeing it right now and typing frantically in the chat window. It seems to have worked first time though, which is fantastic. Like I said, we can up the difficulty. It's harder. If I do difficulty hard, it will try now every possible direction. And this should be rather challenging. Let's see if I can spot any when we do it in hard mode. Ha! There's London going forwards. Hurrah! There's Madrid again going forwards, which is fine. There's Warsaw. Are there any going backwards? Oh, it's hurt my head slightly. Going backwards. No, I can't see any going backwards. In theory, it should work. Upwards. Oh, there's Copenhagen. There's Copenhagen going down the way. Oh, it's really hard to read in a fixed size like this. Any going upwards? I haven't seen any just yet going upwards. Nope. Anyway, you get the idea. I'm not going to sit here and solve this word search for you. Let's try it one last time so I can spot any easy ones going up the way. It does diagonal ones too, which there's no way I'm finding that this time. If you're going down the way, Belfast there, and Cardiff's on there as well. Anyone up the way? Come on. Oh, there's Tallinn. Tallinn. Go up the way. Great. So it is working nicely across difficulties. And there's London going backwards to top there. Fantastic. Whew. Okay, how are we doing? Whew. 7:05 already. Okay. I can't go any faster. Trust me, I cannot go any faster here. So the next step is to make this thing render PDF, because just having a printout into the terminal is not very useful. We want to really have this thing as a PDF. So rather than having, make grid and then print stuff out, we want to have actual rendering. Oh yeah, Warsaw's their second line backwards. Thank you very much, Metal Record 74. Anyway, we're going to go down and add a new method down here called funcRender. It's going to render this thing to a PDF, which will return a data instance, which is the encoded PDF ready to write to disk or whatever you want to do. So we're going to say let pagerect. So a PDF requires space to know how big the page is going to be. This is our pagerect. Depending where you are in the world, you'll have different ideas of what a page looks like. In my case, I'm going to use A4 because I'm from Europe. A4 is natural for us. So I'm going to say CGRect, my size is going to be X0, Y0, width is 612 mils, height is 792 mils. If you are in America, you have to use US letter, but you get the idea. That will tell us the exact size of the page you want to render to. You have to tell that as a part of a PDF. However, we don't want to render completely edge to edge, because otherwise you can't print it out very easily, because printers can't do that very well. we have to attach a margin to the top and the left and right and the bottom, just to pull things in from the edges slightly. So I'm going to say let margin equals our page rect width divided by 10. It's complaining about CG rect. I haven't imported UI kit, which is what it's complaining about. I'll go ahead and import UI kit up here. UI kit, better. So we're going to take 1/10 of our page rect width as our margin. So it'll take whatever size it is and get a bit of margin either side. So for larger pages, there's more margin, which makes sense. What that leaves, though, once you take the whole page size and subtract the margin either side, that leaves our available space, the bit in the middle, excluding the margins. So I'll say let available space be equal to page rect dot width, the full size of our page, minus margin times 2. Because the left margin and the right margin. The middle bit is our available space. And we can then say, let grid cell size, how big to make each square in our grid, equal to available space divided by CG float grid size. So we know how big our available space is, like 400 points, for example. We can then say we have 10 grids, 10 rows and columns on our grid. Therefore, the grid cell size is 400 divided by 10. So it's 40, 40, 40, 40, 40, 40, 40, and so forth. So that's our grid cell size, how big to make each square in our word search. The next step is to start getting some fonts. We can start rendering things to the screen. We're going to say let grid letter font equals a UI font dot system font of, I'm going to do size 16. It works well enough for all sorts of sizes of grids. You can experiment in your own time when you want to, it's fine. We can then say we want to render our letters like A or Q inside the grid space centered. So it's not stuck on the left, it should be centered in the middle of the thing. So we'll say let grid letter style equals ns mutable paragraph style. Grid letter style dot alignment. Alignment. Oh, style, sorry, style. Dot alignment equals dot center. So center the text in the square we have. That exactly is all we need to render any square in our grid, A, Q, whatever. The font is going to be and the rendering alignment. So we can now put that inside some attributes for attributed strings. We can say let grid letter attributes equals an array of ns attributed string dot key. Colon there. Colon any equals dot font is going to be the grid letter font, and paragraph style, comma, that's why, the comma there. Paragraph style, come on, paragraph style equals grid letter style. Edinburgh is diagonally from the top right corner, is it? So it is! Look at that! EDINBURGH, down and left. Sneaky. Good spot, Simon Wolf. It's very clever. It fills it in. You can see it's reusing one of the letters from Tallinn, reusing the N from Tallinn, and so is Berlin. Look, there's Berlin there as well. So Tallinn goes up here, uses the N. There's Berlin using the N, and there's Edinburgh using the N. That's super nice. Anyway, brute force algorithms are amazing, aren't they? They're so cool. They do a great job. Anyway, that is the style to render any grid of our thing in, which is fine. Now the actual rendering, symbol no equals. What did I do? Blah, 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 blah. Fix. Fix does not work. Cool. What did I do? It's complaining at me and people tell me what to do. That looks fine to me. Why are you whinging? Oops, font. Oh yeah, comma there. Sorry, not colon, comma. Comma. Go on. Still not happy. What am I doing wrong? Equals. Does look fine. But fix does absolutely nothing. Thank you very much. ns string dot key. That looks fine to me. String key. Colon any No. Oh, sorry. Oh, I see what you're trying to tell me. Sorry, you're absolutely right. Sorry. Thank you very much. Who was it? Who was it? Who was it? Omar. Thank you very much, Omar. You were absolutely right. I totally missed that. I am obviously losing the plot slightly. That is what's required to render our thing. Whew. Now for the hard part. We actually have to make this thing render into a PDF. And as of iOS 10, we have a new fancy pants UI graphics PDF renderer for doing PDF rendering, which is great. So we'll say let renderer equals a UI graphics PDF renderer with our bounds being our page rect. Give it the whole page to work with. Then we'll say in there return renderer.pdf data and use a closure for this ctx in like that. So this will return the output from our whole PDF being rendered. This is a much nicer way of working. The old sort of UI graphics create PDF context of data was nasty. It was all optional. It may have failed at any point. This thing will always return a valid data instance to work with. It's a much, much nicer way of working. Anyway, so this will start doing a PDF. And now, I told you at the very beginning, we said we're going to make unique instances of our word search. So we can hand out 30 copies to 30 different students, and they're all different. So they can't copy or cheat, whatever. So we're going to say for underscore in 0 up to excluding number of pages, the property from our type, ctx.begin page. Start a new PDF page each time. And then for every new page, we're going to say make grid. Now I've used underscore here because make grid returns a value of the words that have been used. I'm not going to be adding to my PDF, but you can do that in your own time perhaps. You can render in below labels of all the words or clues, whatever. Shiketsu88, what is CTX? So it passes to you the PDF rendering context to draw with, which is a very, very thin wrapper over a CG context that we can do our drawing operations with. We do care about it though, we're using it now in fact. So that will get a random grid for this page, for the student, different every time. We'll then go ahead and start writing the grid. I'll put a little comment here so you can see what's going on. Write grid here, like that. We'll go ahead and say for I in 0 through grid size. So this is literally going to write the grid out, all the lines out the way. It's going to go from 0 up to including the grid size. It's going to go one beyond. If we have 10 columns in our word search, we need 11 lines. So we're going to go 0 up to including grid size. So it'll do one more than necessary. In there, we'll say let line position equals CG float of I times our grid cell size. So it'll move down each time it renders a line or a column by how big the grid size is. We can then say move to the starting point. So I'm going to say ctx.cg context, that's a lower level CG context, dot move to a CG point, which will be our margin for the X, start on the left edge, and Y will be our margin plus the line position. So it will move down each time as we're drawing these rows going down the way. And we'll then say ctx.cg context dot add line to CG point. X is going to now be our margin still, but the total size of our grid as well. So our grid is 10 items, say for right now it is, and our grid cell size is 40 points. So we'll do 10 times 40 and do that as our finishing X, sorry. So add line 2, margin plus CG float, grid size, times grid cell size, like that. That's the X position. And the Y is going to be, again, margin plus line position. So it'll move directly across the way for every given row. So draw a line here, move down, line, move down, line, move down, line, move down. Drawing sort of 11 lines down the way like that. We want to do the same thing, of course, for the column separators. So the same sort of code again, just with X and Y flipped around. We'll do ctx.cg context dot move to CG point. X is going to be the margin plus line position again. Y will be our margin, like that. So we start, and the end position is going to be CG context dot add line to CG point. X is our margin plus line position, because we aren't moving the X, we're just doing down the way each time now. With Y being margin plus CG float, not CG float max, CG float, grid size times grid cell size. Boom. Something like that. Yep, seems to compile. What could possibly be wrong? So that's going to draw our grid lines. That's drawing literally the grid. The next step is to draw the actual letters inside the grid. So we'll do another comment saying now we'll draw the letters. So in this one, we want to draw a letter, move a little bit, draw another letter, move a little bit, draw another one, draw another one, draw another one, new line, draw another one, draw another one, new line, and so forth. All the way down, drawing letters as we go, sort of one pass ideally. So we'll start off by saying our X offset is equal to our margin. Start on the top, that's on the left corner, and then our Y offset is equal to our margin. Start on the top corner. So it's collectively start on the top left corner. We can then say for column in labels and for label in column, go over all the columns and all the rows inside those columns. We have to now get a letter. Say, okay, we've got Q or M, whatever. Read that letter and figure out its size in the space we have. So it'll say, okay, I'm a font size 16, I'm centered. This is how much space I need to be rendered with. And this is important because in core graphics and in fact in UIKit, we can center things horizontally very, very easily. We'd say center it, and it does do. That's what our paragraph was doing. But centering vertically isn't the same. We've got to do that by hand. So when we get our cell size, we'll say, okay, here's a space for a letter. Put A in there. It will render centered horizontally, but vertically at the top, which we don't want. We want to get its size of the letter, like I'm this big, and figure out how to center it with that size. We're basically going to get half the size, move it down by half the amount to get down to centered right in the middle, right at the top. That's the plan. So we'll say, let size equals the string form of our label.letter, because characters haven't got a size, sadly, dot size with attributes, our grid letter attributes. So for this font size, how much space do you need? Now, realistically, for a given letter, uppercase, of size 16, they're probably all going to be the same size, like vertically. But we'll do it in a loop here, it's fine. So we'll get the size of the letter. We can then say, let our Y position, where we're going to render vertically, be equal to our grid cell size minus size.height divided by 2. So half it. So we have our cell size of say 50. We have our letter size of say 20. That leaves 30 left over. And we halve that to make 15. So rather than putting the thing at 0, we'll put it at 15, which means it'll go 15 and then down the way to 45 or so to make enough space to render it nicely. So it's going to render it centered inside the available space. That's what we're trying to do here with the divide by 2. And finally, we can get the full cell rect. Exactly where to draw this letter is equal to a CG rect of our X offset, which is our margin, but moving to the right slowly, plus our Y offset and our Y position, where to position this individual letter, with the width being our grid cell size and our height being our grid cell size. And that is the place to render this particular thing. It's complaining. I make some sort of fundamental mistake. Oops, yeah, sorry. Labels be nice. Y is that, width is that, height's that. Better. Good, okay. Now we can draw our string into that space. So I'll say string label.letter dot draw in that cell rect with attributes our grid letter attributes. And finally, now we've drawn one letter, we're going to move along slightly. We're going to say X offset plus equals the grid cell size. Draw the next letter at the next position and so forth. So it'll move neatly along the whole grid. Once it finishes that loop, once it finished one whole column of stuff, we're going to reset the X offset back to the start of the line again by doing margin. But now, add to our Y offset the size of grid cell size. So move down 1. It's like pressing return on a keyboard. Goes to the start of the line, goes down 1 line. Every time the loop goes around. And that ends all those loops all the way down. And that actually ends our rendering method as well. So that's only 20 past 7. So now, hopefully, we can call that and get a PDF back. I say hopefully because, it's a lot of code. Who knows what could go wrong. We have back in Swift, we call makeGrid. We don't call that anymore. We're going to call makePDF instead, or also render, sorry. And we'll write that somewhere useful. So I'm going to say in here, my old pal get documents directory. We want to find where the user's documents directory is. So whether it's on a simulator or a real device, there's still a documents directory for our app we can write to freely. So we do let paths equals filemanager.default.urls for.document directory in.user domain mask. That is the magic command, which I pretty much got memorized, to tell you where the document directory is for our app. And we'll return paths 0. This whole thing will return a URL. This will tell us exactly where we can store stuff for this user for our app. So we don't want to try and dig around directly. We want to know, just tell me where it is, please. That's what it does. Finally, all being well, we can now say our word search, I want to make a grid. I'm going to get rid of that and say let output equals word search.render. Render the whole thing to a data instance. And then get a URL. I'm going to do get documents directory dot appending path component output.pdf. Boom. That will tell us user document directory is slash who knows what long massive URL. Append to that output PDF. And finally, we're going to try output.write to that URL. I'll build that code. I'm going to do a print of that URL so I can find actually where it's going to save this damn thing. We'll see if it works or not. And I'll press Command R. It's going to build and run. We are 20 minutes over despite my speed talking. It has written something out here. What's it written out? It's written this massive long URL out here. Let's see if I can go to that directory. Let me open up a terminal window. Terminal. Can I open that directory? Let's find out. Where are we? Terminal window. Oh, open output PDF's there. Open that in Finder. There's a PDF and another sip of my wine first. Here we go. Oh, okay. So we have no grid lines, but we do have a word search. I'm almost there. It's working more or less correctly. And they're all, if you look carefully, they're all unique. This has got Madrid in the first line there, and then, oh, come on. Oh, it's on hard mode still. Oh, it's Berlin's down here. And the second one, we're going to have Paris is going up the way in the right here, Budapest across the bottom, go down one further. We have Berlin on the right, we have Dublin on the left. So everyone is completely unique. I have completely muffed up the line drawing code. Go me. We'll look at that in a second perhaps. But you can see it's made however many pages of PDF, which is fantastic. All of which have completely unique word searches from the same thing, which is great. So let's go and look at what I muffed up in the code to make the PDF. A guess from Felipe: grid lines, width, and color. Possible. I didn't provide that, but I'm pretty sure the defaults are sensible. But I might be wrong. Where are we? Hooray for comments. So you can see we've got this right grid comment. We start our grid lines. We loop from 0 up to including grid size. Get our position as being CG float. Start grid size. Looks good to me. Start with margin and margin plus line position. Add line to margin plus CG float grid size. Yeah, more or less looks correct. None of them are drawing though, so there could be the color thing. You could be right on that front. If we did something like, oh, I know what it is. Oh, no, I know what it is. It's not grid lines and color. I'm being a fool. I'm being a fool. Fool, I say. When you call move and add line, you don't actually draw any lines. You're just drawing them theoretically. You're adding a path to draw, and we haven't actually told to draw the path. So we added all this careful grid line path and not actually drawn the path. which is a fundamental mistake to make, so it's not drawing anything. David's now guessed that. Yes, you have to stroke them. Thank you very much, David. We're going to say ctx.cgcontext.stroke draw the path we have added. As well as that, we'll do one more thing, which makes it look a little bit better on the screen. We'll do ctx.cgcontext.setLineCap, which decides how the edges of lines are done. And you can have rounded and similar and so forth. In this case, the best one to use is dot square, like that. That'll look significantly nicer than using like round or something. Anyway, I'll build it again, and this time it's going to work perfectly first time, he says, hopefully. Okay, let's run it again. And in Finder, output PDF. Oh, yes, win. Okay, we now have grid lines. This is a 100% better word search. So again, we have, there's Warsaw backwards across the top. We have Dublin down there like that. There's probably a few diagonals I can't see because I'm going blind at this point. Oh, there's Berlin there, bottom left. Go out of the way, Berlin. That's why it's always good to test on easy mode. There's Vienna. We're using one of the ends from Berlin, which is lovely, which is really nice. So as you can see, it works brilliantly. And again, everyone's different. So you can hand out these 10 pages or 20 pages or 100 pages if you want to students in the class, and they cannot cheat. Okay, that finishes the project, quite frankly. That took me half an hour more than planned. I apologize for going over. But we have made something actually commercially useful here. You could take this and ask users to, input their own words and their own clues, render across the bottom if you want to, add a fancy title or a logo, whatever, and hand out to a class full of students and know for a fact they're all different, which is fantastic. They can do it all on their iPad. So by all means, I'll put this code on GitHub shortly when we finish the stream. Steal, take, reuse, however you want to. It's your code now. They're all free to use however you want to. Go ahead and release any apps you want to based on this. And that finishes the app for now. Now, after the app's finished, now we're here, this is your chance to ask me any questions you have, off topic or on topic, I don't really mind. And I'll do my best to answer them. I normally allocate around half an hour or so for this, so go ahead and use the chat box and I will do my best to answer your questions now. So Ankit's saying you might use a very less number of words. You could do. In the 100 Days of Swift, I provided 50 words in a 20 by 20 grid, and they were beautiful. I mean, they were just brilliant. There was one, I don't want to say which one, but it's a 6-letter word, and it was going up and left and diagonal, and 5 of the 6 letters were using other letters from other words. It was really intensely packed in. So yeah, it was a brilliant word search. And this algorithm, trust me, it's lightning fast. You put that on an iPhone or an iPad, it will do 100 pages in a blink of an eye. You still do it in a background thread, of course. Don't do it in a foreground thread. Background thread's fine, but it'll do it lightning fast. So I really recommend you give it a try. Simon, I'm glad you liked it. It was normally we try and go slower. Normally I try and produce a simpler project to work with so I can talk more slowly, explain what's going on more thoroughly. But here I knew for a fact this was a lot of code. How much code was this in the end? It was 232 lines of code plus some white space and comments and stuff. So a heck of a lot of code. So I had to go at lightning speed just to get through it. Even then it was 20 minutes over, despite my best efforts. Question from Cyril. What is a hash value? Good question, Cyril. If you imagine you had a 25 gigabyte Blu-ray movie or PS4 game or something like that, and you want to know for a fact whether your copy of that is exactly right, you either go through every single bit in every gigabyte of data, or you get a hash value. And a hash value uniquely identifies data. It'll look at 25 gigabyte of data and say, okay, the hash value for this is 64ABC F369, whatever. That is unique hash value for that massive amount of data. And you can say, okay, does my hash match your hash? Yes, boom, it's fine. I've got the right data. And they're very, very commonly used to say for verification of data. So if you download a massive, like a Linux distro, 8 gigs, whatever, you can say, does my hash match your hash? Yes, it's secure, it's good, it's correct. Without having to go through every bit of data. Now, obviously, because 25 gigs of data I can show the bottom of view controller Swift again if I can. There you go. Because you can't fit 25 gigs of data into like 40 letters, there's a chance of collisions. In fact, so Git uses hashes for its commits. So the commit, each commit you make has a unique value using the secure hash algorithm SHA. And I've made commit F694B, whatever, my commit number. And someone found a collision. These are very hard to do. This PDF and this PDF make exactly the same SHA hash, which is very, 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 very hard to do. They found it. And brilliantly, someone tried to put those into Git. And of course, Git couldn't handle it because it went, same hash, same file. It did not understand. So it's basically a way of representing large amounts of data using a very small amount of data, nearly always uniquely. That's the idea. Any more questions? Could we turn letters into a line drawing for printer-friendly PDF? It should be PDF. It's as you can zoom in all you want to. If I zoom in here, Manuel, these are indeed beautifully rendered PDFs. They're lovely and smooth. They're all zoomable, scalable. They're all vectors. It's PDF, so you can do what you like with it. It should be great as a printer, no matter what resolution you choose, which is fantastic. So, Mark, my 50 words code was not exactly the same. The algorithm was the same, but I I wanted to really push your skills a little bit, right? So I wrote a thing. I modified it slightly so it would prioritize placing the most words. So I don't want 20 pages. I want one page, one word search. But I ran it 10,000 times to place as many words as possible. So the number one constraint was how many words can I place? And my goal was 50. But there was a secondary constraint, a sneaky constraint. I want to really make you work hard, where I maximize the number of letters to be filled. So basically, after it placed all the words, as best it can, it placed like 49 words, whatever, it would then go ahead and fill the grid with letters like A, Q, Z, whatever, spare spaces and so forth, with that fill grid method. And I'd make that store how many letters it had to fill. So it would say, I filled 50 letters, I filled 60, I filled 70, whatever. And then I made a secondary constraint be, choose the one that placed the most words and had the highest fill rate. Because the highest fill rate meant it had the most letter reuse. So it'd try and place all 50 words and maximize the highest possible fill rate. So I'd say, I filled 80 letters, which is much more than 50. So it means letters are crossing over more to be extra hard difficulty. So I basically left that. I was sat there at the world's worst airport, which at least in my eyes, the world's least favourite airport, Munich Airport, trying to eat their hideous rock-hard bagels and their awful coffee, running this thing 10,000 times, trying to make the best PDF I could to really challenge your skills. So that's why I added to that functionality. Run this thing 10,000 times, trying to place the most words possible, while also reusing letters as much as possible. Any more questions? When a switch case only executes one command I put on the same line. So Thomas, you're not wrong there. You know, style's very personal, and what you find readable, someone else say isn't readable, and that's fine. I don't often do that, but if it's trivial things like that, I might do it. I think I did it in one of the 100 Days examples. Because it was like getting an album of Taylor Swift. If it's this year, return that string. Some other year, return a different string. I do it there, I think, but broadly, I wouldn't do it. But it's down to you. Style's very personal. Christian, have the same enum structs and classes as the word search file. So really, if this was a word search app, just for doing word searches, I'd put them in different files. Because they are different things. I'm just being lazy here. It's a live stream. I already was over. I knew it was being over, so I was being as lazy as possible to try and save some time. If this was not a word search app, if this app had other things you could do, this thing, you make an app for teachers to generate activities for students, right? And it might do word searches, but it might also do crosswords. It might also do other things, right? Anagrams. In that instance, I wouldn't want to have these things separate because it would pollute the namespace. What I'd actually do is I'd make them nested types. I'd go into wordsearch.swift and I would move these things like placement type, just grab that whole thing and difficulty and word and label and put that inside the word search class so that it was word search.placement type, word search.difficulty, word search.whatever. So it didn't confuse the crossword code or the anagram code or whatever the code elsewhere. So it kept it simpler and cleaner. But if there's just a simple word search app by itself, different, it'd be placementtype.swift or difficulty.swift and similar. Cyril Garcia, what is the in-out keyword of a parameter in a function? What it means is if a parameter is marked in-out, when you modify that value inside a method or a function, that change remains active outside the function as well. Normally, though, it gets passed in and gets modified internally, but those changes don't reflect the outside world. With in-out, it does. It passes in directly. In-out is ever so slightly faster than a regular parameter pass. Richard Lowe, is it easy to render the PDF in a GUI? Yes, it is. It's super easy. Super easy. Good question. There are a few ways you could do it here. You could use PDF Kit. It's fine. It works great here. You could use a web view. Web views render PDFs brilliantly. You could use Quick Look. Quick Look's fantastic and free. So there's 3 different ways of rendering this here, all of which work great. And I've taught them all previously elsewhere. Question from Conrad. In which industry or area do I think AR apps will become the most common? Right now, none. I mean, it's really struggling to make space. And everyone's saying, when Apple finally make Apple glasses, that's when it'll kick off. And of course, they're right. Until then, it's kind of struggling along. It's going to make some impact. I saw some folks talking about it on, we did a sort of a coffee episode on it briefly. And so saying something like, I think for mechanics, it was really good. So you sort of see inside the car more clearly. But whenever I see those dub examples of folks holding up iPads to play games, I just feel really sad. That's a terrible example of how to use ARKit right now, until of course glasses come along. Why choose to make some of the methods private? Only because they have no real purpose publicly. I wouldn't want someone else to call labels from. It makes no sense to expose that in the API here. And normally, if I was doing my own code, I wouldn't necessarily add private everywhere because I'm just doing it myself. But for a public project, this makes no sense to be able to call labels from anywhere else apart from a word search. So yeah, I'd use private there and print grid. I mean, that could be public if you want it to be. That makes sense if you want to print it out. But fill gaps does not make sense outside of the word search type, so I'd leave that in there. Same for try placing. Same for place. I need place words. Most of them make sense as private. Any more questions? This was another lightning fast Swift on Sundays, by the way. And even then it went over. Figures. Oh well. Last chance for questions. So what I'm going to do is I'm going to place the source code onto the GitHub repository. I'll link to it on Twitter again or on the Slack if you're on the Slack group. And you'll be able to download it, try it yourself, modify it. Please ship it, whatever you want to. It's your code now. I don't really care what you do with it. Make it something real because this could really, really work, I think, as an application example. Brand of the wine. I think it's Beefsteak Malbec, if you're really desperate to know. Want to do another coordinator? Probably not. I think I've covered that in my videos already, coordinators. If there's something I've missed off, then let me know. I can try and do a third video perhaps. But broadly, it's not something I want to return back to. Question from Gistech. What industry uses hash values? All of them. All of them. I mean, Swift uses hash values all over the place. When you add an item to a set, it uses a hash. So it can find the object quickly inside the thing. David, Super Chat, thank you very much. I'm glad you enjoyed it. What's special about AR glasses? Well, it stops you having to hold up your device. I mean, like seeing kids, or adults, dub, playing Lego and holding up an iPad just feels really sad. Because you've got an iPad getting in the way of the actual Lego. And that's really sad. So at least AR glasses, you put them on and you forget about them. You just sort of see the world around you enhanced by, Magic Leap style AR, which is much better, I think. The Slack group name is called Hacking with Swift. I can try and send you an invite for that, Rick. I can paste it into the chat, perhaps. Let me see. Invite people. Invite link. Copy that, and then paste that into here. Boom. That is the Slack link there to join the Slack. By all means, come on. ask questions. There is a #100 channel in there if you are doing the 100 days of Swift, by the way. How do I remember all the keywords in Swift? I don't know. I've been doing Swift since day one, remember? I've had quite a long, old while of time to memorize them all. So, yeah. I wouldn't say necessarily it's important to memorize them all. You know, as long as you know where to look them up, you'll be fine. And if you go to hackingwithswift.com/glossary, it lists, I think, most, if not all of them, with my glossary of Swift terms. I'll try and share with you. Oops, Daisy. Like you to there. Boom. There we go. Go to there, and you'll see it lists like most of the terms in there. So you can find them very, very quickly and easily in one big place. So you don't have to memorize them all. I do, because it's just my job. But if it isn't your job, don't bother. Just look in the glossary. Much easier. Any Sprite Kit Swift on Sundays planned for the future? I think so, Smongo. I think so. I'm a bit worried that folks won't turn up. I kind of think folks prefer actual valuable, here is some, you know, PDF generation is a useful skill to have. Functional coding is a good skill to have. I can see there being actual useful things being applied from this. Even if the actual finished project isn't interesting to you, you can take parts of this and use it elsewhere. With Sprite Kit, you've got to want to do Sprite Kit. So I may or may not do Sprite Kit. I might give it a try once and see how bad the attendance is. If it's terrible, I won't do it again. If it's good, then we'll do it again. We'll make some games, because I've got stacks of games ideas. Games are great fun to program, obviously, and they're very visual, they're very fun to test out and so forth. So we might do games at one point. I have no plans just yet. Alan Hughes, do I find it difficult switching between languages? Yeah. If I do a language for a long period of time, yes. And I've done stacks of Swift, Objective-C, Python, C++, you name it, I've done it. Lots and lots and lots of many languages. And you get very good at them, right? You know, when I'm sitting there, I've done Python extensively for a long time. I get pretty good at Python. And then when I pause it and come back to it in 6 months, 9 months, a year, my brain has just ejected all that Python code. It's gone, doesn't exist, gone. And I have to sort of re-import it. And you remember large parts, of course you do. And it kind of comes back to you as you work. You get up to proficiency again very quickly. You aren't sort of relearning it every time. You sort of get up to where you were in a few days or so. But I think keeping all that Python, all that PHP, all that C#, all that whatever, at the same time is very, very hard indeed. I wouldn't recommend it. How do we have two different views in one controller and not as sections? Well, Edison, you could use view control containment. That's a good idea. Adding a child view controller. I should probably do that on a Swift on Sundays, actually. That's a nice topic to do a Swift on Sundays on. Something like, you know, let's get this view controller down to bits using view controller containment would be a good idea, I think. But we'll see. I haven't got plans for next week yet, so maybe that one. Who knows? Question from Junaid. Most of the apps send notifications to users. Yeah. Is that a question? That's not a question. Okay. Manuel. Will there be a certain studies about keeping the identifier of in-app purchase in a keychain? No, there won't be. No. In-app purchases are hideous. They take a lot of work to set up. I might do a video on them separately, but not a live one, because that involves using iTunes Connect Live, which I would not do. Would not wish that on my worst enemy. Honestly, though, it's not very hard. You know, when you get your store kit callback back with an SK receipt, write it out using the keychain. I mean, I've got project, what's that, 28 in Hacking with Swift, covers keychain stuff. Just use that. It's really easy. Just Tech, do I make Android apps? I did make them. I don't make them anymore. Thank you very much. Junaid, I'm not sure what the question is, Junaid. What is the question? There's not even a question mark in there. If you could make it a question, it'd be helpful, that we can answer it more clearly. Question from Zach. Do I have tutorials about encoding JSON and appending the results to a file? Is it covered here? I don't think I have any particular ones that I'm writing out. It's not terribly hard, though. I mean, you know, we have our array of words. Here we're loading it back. We could have just said JSON encoder dot encode our array of words. like that, and it's used obviously a try, do whatever, oops, do, try that, catch errors, like that. That's kind of it. To append to a file though, obviously you want to make sure that you are appending the JSON correctly. So you want to decode the value into a JSON array or whatever, append your items to that, then encode it back into there. We can't append words right now because words only conforms to encodable, or decodable, sorry. So if I just make that whole thing codable, it will be happier, I believe. There we go. Yeah, so decode it first, append to an array, encode that and write that out. That's more or less how you do it, not terribly hard. Any plans for a core data Swift on Sundays? Maybe when I've gone through all possible other ideas, I might do a core data. No, everyone except CloudKit, I might do core data. Otherwise, not for a while, I think. Edison, yes, you can talk containment is what you're looking for, I suspect. What is the key for becoming a really good programmer as I am? Lots of time. Lots and lots of time. I mean, I've been doing it for like 25 years now. So I think lots of time. There's no easy way around it. I'm sorry, there isn't a one weird trick. Sorry. 100 Swift Day 17. Yes, it's coming out. It's coming out. As I finish this, I'm going to upload the videos. They're all ready, but I don't want to upload them because it takes time. I've got to make screenshots, add some text, add to a playlist, yada yada yada. It takes a bit of hassle, that one. So I want to make sure I got it exactly right. I don't want to rush doing videos because they're up there for life. With Vimeo, which is a very nice platform for doing videos, you can change the video after the fact with corrections or whatever. With YouTube, you can't do that. So I need to make sure it's exactly right before I upload. So I've got to wait for that one a little bit longer, I'm afraid. The Swift networking project. Did I do encoding there? I don't remember. I don't think I did. But anyway, it's not terribly hard to do. That's more or less the code on that screen there. But let me get rid of that again. Boom. Okay, last chance of questions. I'm going to shoot off and put this code on GitHub. When learning, do I just read documentation and come up with projects based on what I find? So, Alan, you know, I do try and make the 100 Days of Swift be fair and sensible and encouraging for folks. You're going to start facing code your own challenges in a week or so, and those will be geared at your level based on what you've learned so far. Here's what you're able to make, all being well. So I agree it's hard to find stuff. What I tend to do, the way I personally learn, because I'm rather at the sort of cutting edge of stuff, you know, I get the new Swift 5 tool chains, I get obviously iOS 13 when it comes out on the launch day. I'm downloading it, I'm trying it straight away before anybody else is, or most people are. So I haven't got any things to read. There isn't a lot of documentation at that point, so I'm usually just trying things myself until I get to work, until I'm happy with it, and I can write about it. A bit of a painful experience, to be honest with you, but it kind of works. Don't do it my way, though. My way is the hard way. That's 10 to 8. Is Swift a faster language than C++? It's a complicated question. Because... So, a few years ago, like about 10 years ago now, crikey, it was a while ago, there was a fantastic series of blog posts from a Microsoft engineer who was writing, I think it was some sort of Chinese-English dictionary thing in C++ for the command line. And he was doing a blog post once every day or week, whenever it was, about his progress. And he was like, I'm doing this, here's how fast it is, whatever. He was benchmarking his time as he was going, and going along from there, and marking his progress, which is fine. But what happened was, he said, okay, it takes me this many seconds to load my content. This is really slow. I've got to get better. That was week 1. And what happened behind the scenes without him realizing was another MS engineer in the C# team, the .NET team, was doing the same thing. He was saying, I'll make the same Chinese English dictionary in C#, using .NET, the whole, interpreted language, MSIL framework. And what happened was, on day one, the .NET engineers was significantly faster. I mean, 100 times faster. Something crazy, crazy, crazy faster than the C++ persons. And what happened was, blog post 2 came out, C++ got better, 3 came out, 4 came out, 5 came out, and so forth. The C++ guy kept on adding new stuff to make his code faster and faster and faster and faster and faster. And the C# person was saying, yep, mine's still faster, mine's still faster, mine's still faster, faster, faster. His was faster again and again and again, until finally the C# person had to replace the new operator, the memory allocating operator, had to do his own custom memory allocation to make his version faster than the C# version. At which point C# goes, okay, I'll now optimize my code. And he's got faster again. Now, ultimately, C++ won in that particular fight. Because at this point, he was doing so much work to make his code extremely optimized that it was almost native code, right? Almost machine code. But what matters there is that most of us aren't experts in C++. We're sort of regular C++ users, or maybe good C++ users, but not expert users. And we are in the sort of C# camp. We've got this interpreted library of stuff, and we get that performance advantage out of day one. Now, what's happening was, of course, he wasn't writing particularly great C#. He was writing average C#, but behind the scenes, all those engineers who'd written the sort of C# and C++ layer for doing loading of stuff and file systems and so forth, they'd have done all the hard work of making it extremely optimized. And he was getting all their work for free by using C#. So by writing fairly average C#, he's getting extremely highly optimized code. And that's what we benefit from. We benefit from all the serious work that standard libraries happen for us automatically for, BMW i3, you're going to just go away. I don't care you are going to go away. You're in timeout. Ta-ra. I have zero tolerance for losers like that. Sorry. So we get all this amazing optimization free of charge. And that is a Swift standard library. We get all the benefits of that. All that amazing performance time we have has already been done for us. So by default, yes, Swift's extremely fast, probably faster than C++. But when a C++ expert sits down and writes very, very, very good code, overrides a new operator, overrides this, overrides that, whatever, optimizes the heck out of it, yes, it will totally beat Swift. Of course it will. Because it compiles down to extremely optimized code at this point. We've got 20 or 30 years of experience there doing very, very fast C++ compilation. So yes, it is going to make better code. However, for most of us, Swift's probably faster. Sorry, I know it's a simple question. That's a long-winded answer. I had to go do my best. All right, I think that's it for questions. By all means, follow me on Twitter. I am 2straws. Join the Slack group, ask questions there. I posted the 100 Days of Swift in about 30 minutes, so being well. I look forward to seeing you all complete that. Thank you very much for coming. Thank you for sticking with me for a very, very long stream. I look forward to seeing what you do with this project and hopefully shipping on the App Store next week or next month. Let me know. I look forward to seeing you actually do this thing. Take care. Bye.